So let me go ahead and start. We're right on the half an hour here. So this one is to me very important presentation for not only academic reasons, but because like we hear a lot, especially these days, the cliche that we stand on the shoulders of giants. And this is one prime example on what that is all about. And you're about to hear why. But let me introduce the speaker and the person that wrote this paper, Dr. Marilyn Smith. Marilyn Smith is a professor in the School of Aerospace Engineering at the Georgia Institute of Technology, Georgia Tech, and she's a director of the Georgia Tech Vertical Lift Research Center of Excellence. So that's a big deal. It's great. Only I think 3 universities have that honor. Her research encompasses computational unsteady aerodynamics and aeroelasticity for complex configurations, including, obviously, rotorcraft. She's currently developing reduced order models for nonlinear applications in active flow control, bluff bodies, and turbulence. A lot of aerodynamic specialties here. She is a technical fellow of the Vertical Flight Society, as well as a fellow of the Royal Aeronautical Society and the LAA. What more can I say? Right? She has received numerous technical accolades. The most recent are the 2022 Vertical Flight Society Nikoski Lecture. As you guys know, is our signature lecture for the society, and also the LAA Applied Aerodynamics Award. And this is important, especially for me, the 2023 61st Royal Aeronautical Society Lanchester Memorial Lecture, which you're going to hear about a lot here in a moment. She currently serves as the Vertical Flight Society Board of Directors, and following her stint as the Vertical Flight Society Technical Director in 2020 to 2021. Without further ado, I would like to invite Dr. Smith to the podium. Thank you so much. Please, an applause.
Right. Thank you, everyone. This is a little bit of a different thing for me. It's not computational aeroelasticity or aerodynamics, but during the introduction, you heard I gave the lecture for the Lanchester lecture last fall, and it is typical that when you give that lecture, you go back and you look at what Lanchester did and you try to relate it to your topic. My topic was computational unsteady aerodynamics of separated flows undergoing motion, i.e. rotorcraft. So as part of this, I did a lot of research to understand what he did. And from that research, I said, why don't I write a paper, because so much stuff was new to me, and surely it's got to be new to a lot of the people at the Vertical Flight Society. So, whoops, there we go. Frederick William Lanchester was a British engineer and scientist. He's been described as biographers as well as peers with glowing accolades, which very few people can actually achieve. Now, when you look through here, you see that, very, 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 very dramatic words are being used to describe him, okay? But if you look at it, in history, his name is recognized on various buildings and things, but we don't have a lot of technical names for things that he's done, okay? So he's on a lot of buildings, but why? Because we don't hear so-and-so theory, so-and-so law. No Lanchesters associated with it, right? So what's going on? Then if you look at the Lanchester Memorial Lectures, the very first one was given by Theodore von Karman. It was just a decade after he passed away. And as part of this, von Karman said, we regret that we don't actually enjoy the full recognitions of the contributions that Lanchester actually deserves to have. So what I wanted to do here is, in this paper, is to talk about what are Lanchester's contributions that are specific to vertical flight that we use today, and then a little bit at the end, why isn't he recognized for them? So to start, we want to look at the man. You have, in order to understand his contribution, you have to understand the man. So he was born in 1868 in London, England. He went to the Royal School of Mines and the Normal School of Science, which were together at the time. Today, you might recognize it as Imperial College. Okay, so it's a very, very prestigious university even today. He never graduated. He took engineering, and he didn't like the way they taught the lectures, so he just quit going. And so he left without actually getting a degree. In terms of a career, he was an automotive engineer, and he worked primarily on gas engines. And in fact, you're going to see a lot of stuff where he was very, very prolific in his development of engines. In 1919, he finally got an honorary doctor of law. He really liked that, because then people started calling him doctor. He was also finally named a fellow of the Royal Aeronautical Society, or the Royal Society back then, in 1922, and he got what the Royal Aeronautical Society today gives is they give bronze, silver, and gold medals based on your contributions, and he got the gold medal. He died in 1946 in Birmingham, England, and he was almost penniless at that time, which is very strange if you consider what he actually did over his lifetime. So, to what did he contribute? Well, if you look at automotive engineering, he did many, many fields. He had a number of applications, not only to engines, but to the things that contribute to engines, gears, transmissions, fuel lines, things like that. He also did, as his hobby, aviation, and so you'll see that he has a lot of information, and he has several patents on aviation or aerial machines. He's actually credited with developing the field of operations research. And finally, he had a number of different hobbies, or if something happened with his health, he started getting really involved in that. I think some of us can recognize that. We get obsessed with what happens to us. And so you'll see he had a lot of different papers. He actually wrote books. He was a published poet, and he had a number of different patents, even in these hobby fields. So very, very prolific. So if you look at the patents, you see on the prior slide he had extracts of several patents. He was a prolific inventor. He was granted over 200 patents in Great Britain. The number varies depending on where I look, and I even tried to count them, around 233 to 236. And of those, only 5 were ever formally denied. So he was actually very, very good at that. His first patent was in 1888. He was actually working as a draftsman, because when he didn't get his degree, he had to find a job, so he started working as a draftsman. He hated the replication of drawing the parallel lines and the hatching, so he developed something to make it faster. Sounds like a great engineer to me. And then as part of this, he's got the 233 patents in Great Britain. He also has 16 other patents in other countries. Usually they're duplicative in extending his patents from Great Britain into other countries. He also has 14 that are very specific for aviation, although a lot of his other patents are applicable to aviation at that time. Maybe not today, but at that time they certainly were. Now, something else he has, which I don't list here, is that he actually also had a patent on how to do shipboard landings of aviation. So, again, well before his time. Now, he did so much, so what I'm going to do is I'm going to focus on his aerodynamics contributions, okay, both for analysis and designs, and I'm going to relate the things to rotorcraft. Now, to do that, we have to look at what is his seminal work, which is a 2-volume series that he named Aerial Flight. The first volume was that of aerodynamics. It was published in 1907. Extremely popular, had 4 different printings over the next decade. And it's from this text that most of the things that I'm showing you are derived, because this is one of the earliest textbooks on aerodynamics that was ever published. The ones before were either on hydrodynamics or fluid mechanics, but not aerodynamics per se. His second one was the book that he called Aerodynamics, which is a word that he coined, which means the stability of aircraft during flight. And as you see, this from the Greek, he loved Greek, so a lot of his words came from the Greek that he developed. This was published in 1908. It wasn't as popular, but he did have 2 printings of it. Now, a caveat. Whenever you look back and try to see what somebody contributed, you have to be very careful with that, because you don't want to attribute work incorrectly. And it's very hard because you have to try to see what everybody else was doing. Now, to do this, what I tried to do is gather as much original source material as possible. Fortunately, with the internet, a lot of the early works are actually online, so that's really awesome. I actually got his textbook, Aerodynamics. It wasn't the first printing, it was the 4th printing. But I also looked at a number of his biographical sketches. And so, things that come from contemporary, such as von Karman's lecture. Von Karman did know him. And then some that came later on. Now, in one respect, Lanchester's character made this search much easier because he was known by his contemporaries as someone who was very individualistic, worked by himself. He did not like to collaborate at all. There was one famous collaboration he did, which I'll talk about in a few minutes, but he worked alone. And this was known both in contemporary analysis as well as later on. The later biographers also found this as well. So he did not know what other people were doing. He did not care what other people were doing in a lot of instances. So I want to look at steady aerodynamics because that is what they were studying then. Remember, aerodynamics was in its infancy. So even though we are in helicopters, we look at unsteady aerodynamics. We find our roots in steady aerodynamics. Now, Lanchester developed his own language in this developing field. And in a lot of instances, he ignored the mainstream terminology that people were using from fluid mechanics or hydrodynamics. And that hurt him. He liked to coin his own words. They were Greek. They were somewhat esoteric. His writing was very erudite, so hard to understand. But he still managed to coin some phrases and things that you know. Anybody heard of something called an airfoil? He coined that, the aerofoil in the British sense, but he is credited with the coining of that, and I double-checked that. It's in the Oxford English Dictionary. So, but again, like I said, he relied very much on the Greek. That hurt him because people typically don't like the Greek words. We usually go more to Latin. Now, beyond linguistics, he had two other concepts of aerodynamics that he developed, and that was the vortex theory of lift and the different aspects of drag during flight. Again, we look at some of these today and we say, well, yeah, everybody knows that. But remember, this is when all of this was being developed, so it's quite interesting to look at. Oh, sorry. Forgot to right-click. All right, so the vortex theory of lift, these are, this is the first one I want to delve into. And, remember first, Lanchester was developing this without knowing or collaborating with anyone. He did not have a degree. And so he didn't use the correct terminology. He liked to look at things himself. And this is where he excelled. He didn't develop the mathematical theories. Most of his are observational theories. Now, since he wasn't working with anyone else, he was simultaneously, in a lot of instances, developing things at the same time. So, for example, Joukowsky. One of the things that Lanchester noticed was that, if you've got circulation around a body that's creating lift, then what you'll have is a force that is in the opposite direction. Oh, wait, that's Joukowsky theorem, isn't it? So Lanchester recognized it, but Kutta and Joukowsky actually then made the mathematical representation that we know today. Okay, so this is one of the seminal things that he did. Now, the other thing is, again, you'll see here I've got the word, this is his book, Aerodynamics, so you know that's him. FWL is Lanchester. But if you look at this, you recognize that this looks very similar to the way that we pattern vorticity on a wing, a finite, whoops, oh shoot. Which way? There we go. On a finite wing that we have today. And here you see as tip vortices. You see here distributed vorticity, and it's coming around. So circulation, distributed vorticity. You can see the tip roll up. So here's our tip vorticity coming off. And he also recognized that the three-dimensional aspects of this, he went from 2 dimensions to 3 dimensions, introducing the induced angle of attack and drag specifically. He was looking specifically at drag here. Now, again, these are straight from his book in 1907. Interestingly, a lot of these he developed earlier in a paper that he delivered in 1894, but the Royal Society refused to publish it, so he threw it away. So what we've got here is we've got this material. He was actually known for cleaning house, and he threw out stuff all the time, so a lot of things have gotten lost. Now, one of the things I think is very interesting here that I wasn't able to find any support for, but in looking at it, if you look at this figure right here and you blow it up, and those of you in the back of the room who've taken my unsteady aerodynamics course, if you look here, you see he's taken this vorticity and he's broken it out into its 2 constitutive directions. Well, if you go outboard, if you notice, the magnitudes are changing, and it actually implies that he might have understood the conservation of vorticity. Okay, but I couldn't find any details on it, so I don't talk about it in the paper since I couldn't prove it, but I thought I'd just show it to you here. So I thought that was very interesting, because I think, you look at his sketches and you have to infer what he understood from that, because a lot of times he didn't write about it because he thought you understood too if you were smart. Now, he also had a paper later on in aerodynamics that formed the basis for his aerodynamics theories for the rest of his life. He wrote a lot of papers after that, but you can always track them back to this textbook. Now, he published a very important paper in 1915, and in this, he really shows here, you can see the combination of then bound vorticity and wake vorticity. Again, a seminal theory of what we look at when we are analyzing rotors or wings. Now, Lanchester took his concepts, or he took the basics of his analysis from Newton, and he augmented that by extensions from Rankine and Froude to develop his concepts. Now, here you see then some more information here, and here you see here, did he understand what we understand today when we see something like this? And later on in this paper, this is figure 6, figure 12 in the same paper, what you see here is this is an illustration of how he says the buildup of lift can be made by using these vorticity filaments. So if everybody here is pretty much an engineer, so you recognize then obviously the result that you get when you superimpose all the horseshoe vortices in Prandtl lifting line, right? So you recognize that. Now, this is 1915. It came from 1907, which was built on 1894. So keep that in mind, okay? Now, from this, you have to ask the question then, why do we say Prandtl lifting line? Okay. If you're in the British Commonwealth countries, you probably learned this theory, and you called it the Lanchester Prandtl wing theory or lifting line theory. But outside of the Commonwealth countries, especially in the United States, you don't hear about this. In fact, when I was doing this, I perused a lot of John Anderson's books, which we use quite a bit in the United States, and he'll mention him, but he doesn't really give him the credit that you find here in some of these earlier works. So he's not really known, and that was one of the reasons I wanted to do this paper. Okay, so Prandtl actually released his lifting line theory in 1918, and here's the title of it. And if you translate that loosely, Tony, I see you out there. You can probably tell me if I've got that wrong. But it's airfoil theory, first part, a memorandum. Okay, so he gave both the theory, but, and this is the big change, the big difference, he gave a concise and simple mathematical solution to this theory. Now, in this actual paper, which I did look up, and I actually translated it with some help from Google, Prandtl actually does credit Lanchester for the concept of circulation, but again, he notes that he lacked the quantitative elaboration that was crucial to success. So why didn't he have that? Well, again, let's look and understand what was happening there. Prandtl was a professor at the University of Hanover, and he had his students doing a lot of work on this. And some of the students included Betz, everybody recognizes the name Betz, or Max Munthe. Okay, so he had a lot of students working on this. And later on, in 1927, when Prandtl was giving the Wilbur Wright Memorial Lecture, he noted that, they did benefit from theories from his aerodynamics book, and they were able to draw many useful ideas from his book. Now, this Prandtl, Lanchester was actually one of the few collaborations he did, because Carl Runge saw the book and was going to translate it into German, and they were very interested. And actually, the Germans appreciated the book much more than the British people did at the time, and so they learned a lot from it. And he actually did visit Prandtl and work together, and Carl Runge and his daughter helped to translate, because Prandtl didn't speak English and Lanchester didn't speak German. Okay, so this was very important, and I think it's important to note that even Prandtl gives Lanchester credit for some things, but today, again, in many, many textbooks, you'll only see Prandtl lifting line, and if you see a list of what Prandtl did in contributions, you'll see absolutely no mention of Lanchester at all, unfortunately. Now, the second fundamental area is that of skin friction in drag and separation. Now, the concept of viscosity and no slip were known by Lanchester's time, so he didn't develop that. They understood that, but the role of viscous drag on flight vehicles was not understood at all. In fact, in 1891, Samuel Langley published his book, The Experiments in Aerodynamics, and he said that skin friction plays a negligible role in the total drag of a lifting surface. And that was, Samuel Langley was a big deal back then, and so people accepted it for about 15 years. But during 1905 to 1907, Lanchester did a series of experiments. He used flat plates, and he proved demonstrably that, skin friction, or as we call it today, viscous drag, was critically important. And in fact, at the operating speeds and things that we apply it at, it was key, and it was more important than the drag that Langley was referring to. He also came up with the correct relationships that we see, where this is the viscous drag and this is the induced drag. Okay, they called it resistance. This is why it's so hard to read, because none of the terms are the same that we use today. So the direct resistance associated with viscous drag and the aerodynamic resistance associated with the induced drag. Okay, now everything was still at this point talking about attached flows. Okay, so we don't really call it pressure drag per se, it's more the induced drag. Also related to his vortex theory of lift, because he referred everything to that theory. that's kind of what's beautiful about it, is because everything he did kind of bases on it, and so many things were correct that he inferred from that theory. Now, he also looked at separated flows and STOL, and these are some of the earliest pictures that I've been able to find that indicate what he was doing. So he did it. He has it twice in his book because he's talking about different things. This is more for a flat plate, as you see, and you see here's an attached flow. You see here's a separation bubble. Here's fully detached flow, and you see it with a traditional airfoil shape. Okay, so he recognized what that was, and he also recognized in looking at these in his book, what he was talking about is that you have to have your wing oriented so that you have the top situation and not this situation. Okay, so he recognized that was important. He also recognized an elliptic wing would minimize the drag. Okay, so he did see all this, and this is directly in his book, if you can decipher it in its many language. Now here, this leads to another issue, and that is, I've been talking about the theories, but what about propellers? Okay, how does this work? And this is his application to a screw propeller, and you see he recognized that you could go from trailing vortices, both in translation as well as rotation. And the vortices could be, they're of the same hand. They go in spiral groups, then they break down. Gee, it sounds just like a helicopter wake, doesn't it? And that's what it is. And he said, depending on how you connect to the hub, or as they call it, the boss, then you could have no root vortices, or you might have root vortices. Okay, so again, optimization. In 1915, he gave a paper, again, where he actually talks for the first time about helicopter applications. He recognized that when you were talking about a propeller for helicopters, you're talking about the maximum lift with the minimum power rather than the current applications, which was the largest mass flow rate. Again, in some of this, let me just quickly go through this because I'm running out of time, but he noticed all of these things. If you go through his paper, you'll see all of that information. You'll see he also talked about the optimal efficiency limit. We know that today is the Betz limit. Again, there's been some recent papers in the past 20 years. Should it be Lanchester Betz? And they said, well, at the time there was the Froude and there was the Parsons methods. And Lanchester did a combination of the two where you could go between the two. And recent people, researchers, have said, no, that means he doesn't get credit. And instead, they said, Joukowsky gets the credit. So they said we should call it the Betz-Joukowsky limit. I'm not sure that I agree with that. Yes, he made some errors. A lot of people made errors, but the premise was still the same, and he came up with it himself. But, let's note, too, he made a number of correct assumptions when it comes to helicopter blade design. So he did a lot of work in momentum theory as well as the other, whatever it's called, blade element theory. I'll get there. And in 1917, again, it's important to note that one of his contemporaries says that, they were calling it the air screw at the time, and the only one given is the one given by Lanchester. And we see clearly it's blade element theory, propeller analysis, a step in the right direction. So he did get some credit early on. Another thing that I think is interesting is in 1897, he had a patent. Yeah, I think it was 18. He had a patent called the screw propeller. But look what he did, even though this is an aircraft analysis. He came up with the contra-rotating propellers or counter-rotating propellers. And the reason he said is that otherwise you're going to get a lot of energy loss, so you can capture it. And I thought that was quite interesting that we're talking about well over 100 years ago on concepts that are now considered relatively new and innovative today. Now, he did a lot of other contributions Stability and control, he had that whole other book. Unsteady aerodynamics, W.P. Jones, if you were in unsteady aerodynamics, he's one of the giants. He said he was a pioneer. Lanchester was a pioneer. And Arthur Koller, of course, in aeroelasticity, also said he was a pioneer. The reason is in the 1916, 1917 range, when they were having catastrophic aeroelastic crashes, he recognized that not only do you need to strengthen your structure, but there is an influence of aerodynamics, and it's changing because it's creating this elastic motion. So he's the one that recommended and got the royal, the UK people to study it, okay? And that led to the Flutter Bible, and it led to all the analyses in the 1920s and 1930s by Garrick and the rest of them in unsteady aerodynamics. So I think rightly they called him the pioneer or the father of it. So why don't we recognize it? Well, I mentioned non-standard nomenclature. He worked primarily as a hobby, so he didn't have funding. He didn't have graduate students. He didn't have any of that. But he was also very, very difficult to work with. Towards the end of his life, he was somewhat of a pariah. He loved to battle people. You might know other people today that do that. Yeah, this is probably why he's not. But I do think in the aftermath, looking today, we can step back and take a look and understand and appreciate what he did theoretically without the mathematics, and he understood it without a whole bunch of experiments and without a whole bunch of mathematics. And I hope I've shown you that today, you know, his lifting line theory that he developed, which of course in all of our comprehensive codes was a topic of the Nikolsky lecture a couple of days ago, is very important. So thank you very much. Apologize, I'm a little late.